Okay, I'm starting this lecture, and I hope you all can hear me. I will check to see if the sound is okay. Just pardon me while I do that. About trigonometric functions, and we talked about how to find the values of trigonometric functions for first quadrant, and then to extend that to all four quadrants. And we looked at, we pictured this in terms of graphs. So we drew the graphs of the sine function and the cosine function, and also determined or showed how to use the reference angle for any angle to determine the appropriate values of the trigonometric function in terms of the trigonometric functions of the reference angle. Okay, so you'll remember that the absolute values are the same. You just have to find the right sign for the trig functions of the full angle. Okay, so today I'd like to continue on in chapter 8 and discuss periodic functions, in particular the sinusoidal functions. Okay, so I have sinusoidal functions are going to be like the sine and the cosine functions. They're in general called sinusoidal. So this would be the sine function. Y is equal to sine of x. So here's the x-axis, here's the y-axis. So I'm changing from the t variable to the x variable now, and so I'm replacing t by x here. Okay, and the cosine function looks a little bit different. It's got its peak at the origin, and it goes like this. So they're called in general sinusoidal functions. So they're basically just the sine function shifted around, possibly stretched, shifted in the horizontal direction as well as in the vertical direction, possibly stretched or in the horizontal and shrunk in the horizontal, and also stretched or shrunk in the vertical direction. By the way, reflecting doesn't give you anything different. If you reflect on the y-axis, you'll also get a sine function with the same period and the same amplitude, but maybe with a different shift in the horizontal direction. The shift in the horizontal direction will be called a phase shift. And a shift in the vertical direction will be called, I guess it's sometimes called a vertical offset. But here it's probably just called a shift or a translation or shift in the vertical direction. Okay, so now these sinusoidal functions are to be distinguished from the more general periodic functions. Periodic functions could have any shape besides including these ones, but also besides it. Periodic functions, for example, might be like the tangent function, which has asymptotes, but we'll see like that it looks like this. It has a part that goes between the asymptotes, and that's repeated, and so are the asymptotes in all directions, like in both directions like this. Oops. There we go. All right, so that's, for example, the tan y is equal to tan x. We'll see that later in this lecture, hopefully. Okay, so the general form of such sinusoidal functions is as follows. You would have this form then. You have, including all the possible shifts in and stretches in the horizontal and vertical directions, you have a sine bx plus, or minus actually, c plus d. So that's the general form of a sinusoidal function. All right. Now, from this general, we can read off the features that we've been discussing so far. One feature would be this thing here, starting from the outside and working in. This is called the vertical offset, or the vertical shift. So what that means is the whole thing gets shifted parallel to itself in the vertical direction. So this center line, about which the function oscillates, if you like, will be shifted up to a new level. So it's some y equals d is sometimes called the baseline. All right. Whereas the d itself is the vertical offset or shift. Okay, so now, by the way, A will give you what's called the amplitude. So the amplitude is basically to describe how far the function goes away from the offset in both directions. So the offset is here, y equals d somewhere. Let's say it's up here somewhere. And it goes like this. And so this line, y equals d, is going to be an axis, if you like, of symmetry, because if you flip this curve and just twist it around this line, just flip it upside down where you're using this line as an axis, right? Then it will just become the negative, sort of become just upside down, but in the same line. So you're not shifting it anymore up or down or reflecting it about the x-axis, but you're reflecting it about this line. And so it will have a different appearance. And I'll just use a different color. All right, so A reflects this distance away from, it's the same distance away from the line D. So the maximum you can get if you vary the value of x here, this x, as long as b is not 0. So we need that. So b cannot be 0 here. And then this will vary through all real numbers. This argument will vary through all real numbers. And then the sine function will go throughout its range, which is from -1 to +1. So that will change this to possibly a maximum of d plus a, and a would have to be positive there. So a could be positive or negative in this case. So if a is positive, then the maximum will be at d plus a, and the minimum at d minus a. All right? So here's d plus a, here's d minus a. All right. So that's the amplitude. The amplitude actually is the absolute value of a. it gives you, so it's basically the maximum value minus the minimum value divided by 2. This will always be a positive number, because maximum is always bigger than the minimum. All right? And now another, so that's given by A. So we have D and A kind of explained in these terms here, these kind of physical terms. All right. So if you want to think of some physical object, you can think of a not just, you can think of a wave. Okay, so this looks like a wave on the ocean or on a body of water. All right, and or it could be a mass on a spring. Well, if it's a wave on water, then we'll need to be a bit careful. If you fix the time and then take x to be, change x back to t the time, then this corresponds to a single point on water. It doesn't move at all, but the wave, as it passes by, a little floating object will just bob up and down on the water. And this will be its height above the bottom of the lake as a function of time. Right? So that's one way of interpreting this physically. All right. So let me write that down. So a floating object, which is maybe a buoy or something, buoy. And it bobs up and down, bobbing up and down because of a wave passing by. So a wave comes in, and here's our floating object. So it starts moving up and down when the wave comes in. And this could be the shape of it. If it's an infinite wave, then this would be the shape of it. All right. So the amplitude, that's simply the maximum minus minimum divided by 2. So it's this distance away from the baseline, or this distance away from the baseline. You just take the absolute values of this or this. So if you plug that in, for example, then you get d plus a minus d minus a divided by 2, and so the minus signs here mean it's d plus a minus d plus a. So the d's cancel, which is what we want, and we get a. Now, okay, so now let's look at this part here, the B and the C. All right, so the B refers to the frequency of the wave. As a wave passes by, as the object is bobbing up and down, how frequently does it bob up and down? Does it bob up and down really fast or really slowly like this? All right, so if it bobs up and down very fast, then the graph would look like this. If it bobs up and down slowly, then it would look like this. And the way you count the number, you count it by the bobs per second, or the periods per second. Each of these shapes here, going from the very top all the way to the bottom and then up to the very next peak, is called a period. Okay. This is with the time axis now. I'm measuring in the time with the time axis here. So that's called a period. So when you have a fast rate of bobbing, that means the period is, p is small. The period is the time between two successive peaks. Two consecutive peaks. All right, so here the period is bigger, and the rate of bobbing is smaller. Slow rate of bobbing, and p is small, or big. At least it's bigger than this one. Yeah, I'll put big. All right, so now the way to get an exact relation between b and the period is, when we look at this formula, let's go back to this formula. When the value of the sine function is 1, let's say a is positive here. When the value of the sine function is 1, then this will be at a maximum. Now for that value of x which makes the sine function equal to 1, this sine part of the function equal to 1, for that value of x, that value of, let's make it t since we're using t here. So for that value of t, we're going to have to be right here at some peak. Now we increase t by a certain amount. And that will be the period. So if we increase t by the period, let's call it t0. So it's like a starting time. So t0 is here. If we increase t from t0 to t0 plus p, okay, so I'm just telling you that at that time, t0, we want this sine function to be equal to 1. Then increase t to t0 plus p. That's the next peak. How much does t have to change then by? Well, the sine function, remember that between two consecutive peaks, similar places on the sine function, if we're talking about just x in there, so I'll now call this whole thing x. That is going to be the same as, it's going to have the same value. The sine function will have the same value if I increase the value of x precisely by 2 pi. That's the definition of the period. This is the smallest value for which this is true for all x. This is the smallest shift I make in the function, positive shift I make in the function, which will not change the function for any point x. All right, so when I think of it that way, then all I have to do is change this x. I have to add, I'm taking, oops, I have to have my brackets in the right place. I have to take this value of x, this is my initial value of x, call it x0, and I have to shift it by x0 plus 2 pi. Okay, so that will give me the new value of x which I can call x1. So just to put labels on this, t1 is nothing more than what I've written down here. So, and then x1 is nothing more than this. All right, but so x1 we get by plugging in the new value of t, namely t1. So this will be x1 is b t1 minus c. Okay, so if I substitute, then I get this. Okay, this is a different line. b t0 plus, this is in brackets p, minus c. Well, if I expand the brackets, I get b t0 minus c plus b times p. Okay. So now I'm thinking also of b as being positive here for simplicity. So think of b as being positive. Then the b times p is also positive because p is a positive number. So I am indeed increasing from x0 to x1. So the difference is, and should be equal to, this should be equal to 2 pi. All right. And that means that p, the period, is 2 pi over b. Okay, so let's restate that. Given this form of the function, I start at a point t0 where the sine part is equal to 1. So that will give me a maximum of this function. Y is a function of t. And then I want to increase this argument so that it goes to the next peak. So it's like increasing x from x0 to x0 plus 2 pi. But this function will change by 2 pi when t itself in here changes by 2 pi over b. Okay? All right, so it doesn't depend on c in this case, just on b. All right, so in general, if I've assumed here that b is positive, if b is negative, then I would end up with the absolute value of b here instead of just b. Okay. So this is true for any b not equal to 0. And now finally, the C. The C stands for what's called the phase. Okay, C itself is related to what I would call the phase shift, but it's not exactly the phase shift. So the phase shift, so you start with a standard form. Here we're starting with the sine function, standard sine function. So this would be say sine of t. So this would be y, this would be t axis, this would be pi, this would be 2 pi. So t is measured in radians. All right, so, and it keeps on going in this direction as well. If you scale in the t-axis, in the t direction, along the t-axis, if you scale it, that means you stretch it or shrink it, then what are you going to do? You're going to have to either, if you stretch it, then you're dividing by some constant which is bigger than 1. Okay, so if a is bigger than 1, then let's not. I'll keep this equation the same. So this is referring to this graph. I'll start a new graph here. let's call it little a, so as not to confuse with that a up there, capital A up there. So here you would get, for a greater than 1, you would get a stretch thing. So this would be not pi, but something bigger than pi. And the actual answer would be a times pi. And this would be 2a times pi. Okay, so it gets stretched from here to something bigger than pi, which is namely a times pi. A is bigger than 1. And if you plug into the equation, you can see that this value inside the argument here gives you simply pi. So a pi divided by a is simply pi, which is the same as the t here. And then this part here, if you plug it in, you get 2 pi. So that corresponds to this point here. All right, so that's what I called x over here. I called x the argument. So x is equal to this t over a. So if I shrink by making a less than 1, then I'll get the same values here. So this is greater than pi, this is greater than 2 pi here. But over here, I still get a pi and 2a pi, but these are both less than pi, because a is less than 1 here. And this is less than 2 pi. All right, so it's a shrinking instead of a stretching, just based on whether a is greater than 1 or less than 1. Okay, so now, how to relate that to this form. So in this particular form, okay, I've already explained that this, yeah. So a here, the stretching and shrinking, that's related to the b, which we've already done, the period. But now I want to think of shifting. If you want to shift this whole graph, then it looks like this. So y is equal to sine t minus, let's call it little c for now. So little c. So what does that do? That shifts, if c is positive, it shifts it to the right. If it's negative, it shifts it to the left. Okay. If you're thinking of the bobbing float on water, shifting it to the right here's the actual value of c shown in the diagram. I shifted when it passes through the origin here, it's shifting over this way like that. So for the bobbing float, what it's saying is that instead of starting it at a certain time from the midpoint and then having the wave push it up, it starts a little bit later. Okay, so a positive shift means delaying it, whereas a negative shift means you start early. If c is negative. So that will look something like this. It will start up here and then go down. Okay, so by the way, it's kind of you can define this value of c is called the phase shift. And it will vary between, well, it can be any number, but you can characterize it by a number between 0 and 2 pi. All right. If you have another phase shift which takes you up to here, that's just adding 2 pi to the original phase shift. So you can represent the new function in terms of an infinite number of possible phase shifts. They all differ by multiples of 2 pi. But if you want one in the range here, then there's only one. Okay, or you could also make the phase shift negative, and you can shift it all the way so that it looks the same as that. Okay, but yeah. So again, there are an infinite number of ways of representing the phase shift. Okay, so. But in our case, we'll try to keep it simple. We'll try to keep it in this range. So what you do is you start with a standard function here. And let's now say it's got an amplitude. Let's say A is positive to make it simple, and B is positive, and then you have it like this without a phase shift. And let's say there's no vertical shift either. Okay, so we have this is pi over B. This is 2 pi over B. The period is 2 pi over B. A is the amplitude. Okay, so now when I add a constant inside the argument, what does that look like in terms of t? So if I let x be t, and express this as x instead of t, so x is still kind of a time physically, but it's a scaled time. It's like I'm doing things in slow motion or fast motion. I'm changing the scale of the time. All right, so what happens if I change the scale of the time here? Or, okay, we've talked about that. It's just stretching and shrinking in time. But if I delay this scale time, then the way that it's delayed in actual time is going to be different. The scaling factor will stretch the shift as well. Okay, so the phase shift here is the shift in t well, okay. It's really okay. We want to start with a standard function, and we want to say what the phase shift is for that. And the phase will okay. The standard function will be sine of x. Where this is pi, this is 2 pi, and so on. So when you shift that, then the phase shift can be, say, negative, in which case you'll get the cosine function. We saw that before. So you just add something to x if you want to shift to the left. You add a positive number, and we saw that before. That gave us the cosine function of x, cosine of x. This is just an example. Okay, so that's what we got before. So this is 2 pi here. This is pi here. All right. Now you can also have in-between values. All right, so this means that in general you get this form. So in terms of x, the phase shift would be just delta x. X, remember, is bt. that will simply be minus c. Okay, so since to get from here to here, I forgot my a here. I just have to replace x by bt and then replace delta x by minus c, and then I get this relation here. Then I get from here to here, so that this is a requirement for that to be, to identify what I'm calling this phase shift as minus c. All right. Well, I mean, it's a bit awkward actually to make it positive. Let's keep it negative, and then the sign will be positive here. So now you're thinking of delta x as this delta x will be actually minus pi over 2, right? So in general, delta x is a shift to the right if it's positive. All right. So now in terms of t, what is the change in time that I need to do in order to go from the standard graph? So the standard graph will be in terms of t now. Y is equal to a sine bt. Okay, so it starts at 0 at t equals 0. It has a different frequency than before. So how does t have to, what does this have to be shifted off so that I delay it by a few seconds? So how much is this equation delayed if c has to be positive there? How much is this delayed if I have a c in there? Well, delta x is delayed by c, we know that. Delta x is the change in this expression here. So it's bt minus c. Okay, so this expression here, this expression in here is called, we call x the phase actually. In physics especially, this is called the phase. So I'm trying to show you that when the phase is shifted, then the time also is shifted, and that the actual shift in the phase is equal to the change in time. Oh, okay, let's see. So my full expression for the phase function is this. So if I so in one function I have a particular form for the function of the phase shift. So x in the first case, so this case, x is equal to b times t. Now in the second case, I've shifted it over slightly, so I'm starting here and continuing. In that second case, my phase function is equal to bt minus c. Again, c can be anything. It's between 0 and 2 pi here. Okay, because this, if it goes bigger than 2 pi, remember what we said for x, if the change in x is bigger than 2 pi, then we'll just repeat our phases. We can always describe the phase shift in terms of x by multiplying or adding or subtracting a multiple of 2 pi. So we can always replace the value of c with something between that fundamental period. Now, what is the shift in time that I'd have to perform in order to get from here to here? Well, if you just factor out the b, then I have to divide c by b, and then that gives me the same thing as this function here. So the shift in time is c over b. All right. And so that can also be called, I guess in the book that's also loosely called the phase shift. All right, so now let's look at some examples. So the phase shift is the actual shift in terms of the time. So really this value is the actual shift in terms of time. Right, I'm taking the independent variable to be the time variable or the t variable. Okay. So let's see some examples here. First example is or one first example might be 3 sine x. Okay, so 3 sine x is simply a stretching in the vertical direction. So instead of an amplitude of 1, it's 3. So it's just the absolute value of this multiplier in the front of the sine function. The period is just 2 pi divided by 1, or still 2 pi, so that has not changed. And the phase shift is 0. The time shift is 0, really. And so, yeah, so what I'm saying is that this is loosely called the phase shift, but it's not accurate, I think, in terms, if you express everything as, if the variable is the time variable, then this should be called the time shift, and this combination, because this combination is called the phase. The phase is what you put in for x here. So if you start with just the sine of simply x, you put in this phase function, and that's what's normally called the phase. Whatever you put inside the argument of the sine function or cosine is called the phase. Okay, so change in phase from 0 to 2 pi takes you through exactly one period of the function outside. That's the idea. Okay. So it's also loosely called phase shift, but to be accurate, we should call it the time shift. Okay. So sine 3x has an amplitude now of 3, and nothing else changes. So here's pi, here's 2 pi. So we go all the way up to 1 here, through pi, and then 2 pi here. Oops. Stop at 2 pi. Okay, just putting in the values for the variables here. All right. And what if you have 3 sine 2x, or just sine of 2x? Sine of 2x, y is equal to that. Okay, so what that's saying is the amplitude is 1, and the period now is 2 pi over 2. B is equal to 2 here. There it was equal to 1. So the period is now pi. So we basically get more periods within the same interval. So this will become we'll have 2 whole periods, one going, to make it so high, one going like this, another going like this. That's pi, and that's 2 pi. This is 1 and minus 1. And this I'm taking to be x. All right, compare it to y is equal to sine. Compare it to the standard function y equals sine x. So that's 3 sine x. This is sine x here. So it just has a smaller amplitude, and that's it. Here, the amplitude is the same, but it's stretched out in the horizontal direction. It's shrunk from the horizontal direction. Okay, so this new function is the more compressed one. Then the old function is more stretched out in comparison with the newer one. I guess we get to use different colors here, right? All right, so anyway, I don't want to linger too much on just one thing, so I'll have to ask you to please try to read the textbook as well to if this is still a bit foggy for you. Let's try y equals sine 2x minus 3. Okay, so now this is it's like a shrinking to get this function. So what is the, okay, let's put in our time variable so we're now using the independent variables is explicitly time. So now we have equals 2 sine 2t without the shift is going to be the same as before, except now I'm just thinking in terms of time. So this is one whole period. This is another whole period. So if I shifted time, then delta t will be 3 over 2. So that's the actual phase shift is minus 3. Actually, let's make this a little bit, that's going to be a bit complicated. So I should make a multiple of pi here. So let's make it 3 pi over 2. Okay, so now a phase shift of 3 pi over 2 will do what? It will go from 0 to, here's pi over 2, here's 3 pi over 2. So we'll move this all the way back to here. But with this phase factor in the time direction, this will be c is equal to plus 3 pi over 2. All right? And b is 2. So I divide c by b and I actually get 3 pi over 4. So it's not all that way, but it's halfway. So it gets shifted to here's pi. 3 pi over 4 is, I guess, that is right, yeah. It's right in, it is right here, actually. So this is 3 pi over 4. right? Because this is pi over 2, this is pi over 4 here. This is pi over 2 here. So this is 3 pi over 4. Okay, so actually what I was doing was the phase, I was measuring this phase shift by looking at the full period. I know that the full period is 2 pi, corresponds usually to 2 pi, right? And I'm thinking of pi over 2, pi, and then pi over 2, 3 pi over 2, and then 2 pi. But I forgot that I just changed the scale here. So when you change the scale, the actual change in time will be twice as much, or half as much. So half as much. So I go pi over 4 instead of pi over 2, pi over 2 instead of pi, and 3 pi over 4 instead of 3 pi. So that brings me to my actual starting point, and the starting point the graph will actually start there and then go up and then reach a peak at pi. You just shift everything over by the same amount, right? And this point will get shifted over by, again, 3 pi over 4. So if I don't overlap everything, see it better. So this keeps on going, and this goes in both directions, right? This will be 5 pi over 4. If I go back, then I will reach 0 again back here. It's going between 1 and minus 1. And I keep going. So this first graph is the unshifted graph. The second graph is the shifted one, shifted by 3 pi over 2. I mean, shifted by, the actual C over B, the time shift will be 3 pi over 2 divided by B, which is 2, so it's 3 pi over 4. All right. In other words, take the full period. 3 pi over 2 is 3/4 of the full period, right? Normally, this is, so you go 1, 2, 3. These are quarter periods here. 1, 2, 3, 4. So you go 1, 2, 3, and that's how much you shift by in the time axis. So the actual period is actually pi, not 2 pi here. So you take 3/4 of that, pi, to get the actual shift in terms of time. All right. All right, so now this baseline, it's also called the midline, I realized just now. So y equals d is the base, is also called midline. The midline. Okay, so let's do a try it problem. So try it number 9. Draw the graph. This is on page 653 of the book, Abrahamson. Draw a graph of g of x is equal to minus 2 cosine pi over 3x plus pi over 6. Okay. This is minus. All right, so now, not to worry about the minus. The minus will usually just mean an extra phase shift of pi, overall phase shift of pi here. Or you could just remember that if you take the negative of the cosine function, that will start off at minus 1 at the origin. And then you can shift that in the usual way. So that's minus cosine x, 2 pi, etc. Okay, so draw a graph of this function here. Okay, so now I'm thinking of x as the time variable, not the phase shift. Actually, to make it very clear, people often use the Greek variable phi, Greek letter phi, to represent the phase function, because it sounds like f, the f sound appears in phi. PHI. Okay, so this is how we'll label the phase function then for this case. It's a linear function of x. All right, so in our case, using our definitions then, A, the amplitude, is easy to write down. It's just the absolute value of minus 2, which is 2. Okay, so the max and the min differ by 4. And then you want to find the period. So you take the value of b. That was the value of a. So you take the value of b and take 2 pi over of the absolute value of that of b. So here b is pi over 3. So you take 2 pi over 3. So the pi's will cancel. The 3 will go in the numerator. Okay. So I'll get 6. And then the shift, or the shift in x now, from this, the shift, if this is my unshifted function, it will be shifted in terms of phi, actually. So actually phi should be here instead, right? Let's not confuse phi with x. So the shift in phi will be pi over 6. Actually, minus pi over 6. It's a shift to the left now because the c is negative. C is equal to minus pi over 6. The shift in x is then that c over b. So it's minus pi over 6 divided by pi over 3, which is minus 1/2. Okay, so let's see what it looks like. So you have your x-axis here and your y-axis here. Let's label a few points. So 1, 2, 3, 4, 5. Let's make a 6 there. Let's make it up to 7. And amplitude is 2. So let's take this to be plus 2 and minus 2. And we'll put another one in the other marker here. So it's minus 1. Minus 1, 1, 2, 3, 4, 5, 6, 7. All right, so my starting function without any shift would just be, it would have period 6, and it would be negative 1 at, or negative 2 at x equals 0. So I start looking at this function here. So when x is 0 in this function, then the starting value is y equals minus 2. And then it goes up and reaches its peak halfway through, so that will be at 3, because the period is 6. So it will go pass through the middle somewhere here. And then it will go down somewhere in the middle is right here. So it's these are the quarter periods, by the way. 1/2 is 1/4 6, then 3, and 4/5 is the third quarter mark, and then 6 is the full period. Okay, so these are the max and minimum values. Now, if I want to show the effect of this shift, the shift here is telling me it's in terms of x. So I shift to the half a mark into the left here. Half a distance of 1/2 in the negative direction. So this whole thing gets shifted over like this. So it actually starts at a minimum of -2 here. And then it goes through the through 1 here when it goes to 0. It goes through x equals 1. And then it reaches a peak just half earlier, like this. So at 2.5, it goes down and reaches 0 at 4. And then it goes down and reaches the minimum, or the valley, at 5.5. Right? So all these points just get shifted over. Every one. When I go from this function to this function here. Now we should just check to make sure this is correct. So, and I'm really sure I'm not using different colors. I really should try that here. So this is my new shifted version, final version. Once it goes past this, it starts going up again. Okay, if you have a graphic calculator, that's thing. You know, it's good. You could try this on a graphic calculator if you do have one. It's not necessary, but let's at least check this using some calculations explicitly. So if I plug in x equals 0, for example, in the new function, the green one. Let's use green for a while. So if you check explicitly, x equals 0, what should you get? You should get g of x, g of 0 is -2 cosine pi over 6. But we know cosine of pi over 6, that should be the same as sine of pi over 3, or root 3 over 2. So it's times root 3 over 2. So, and the 2's cancel, and I get minus root 3, which is about -1.732. That you can use a regular calculator to find. That's a scientific calculator. Does that make sense? Yes, it does. Okay, that's about correct, because when you go back through this point here, then the value of y is less than -2. This is -2 right here. You're going to be less than absolute value than -2. That's going to be about right. Okay, let's try 1. So the value of 1 should be 0. So is that indeed what you get here? So -2. So g of 1 is equal to -2 times the cosine pi over 3 plus pi over 6. Okay, so we have to combine these two fractions. That's easy, right? So it's 1/3 plus 1/6 times pi. 1/3 plus 1/6 is 3 plus 1. No, sorry. 2 plus 1. 2 over 6 plus 1 over 6. So I just use the same common denominator. That's 3 over 6, which is 1/2. So this whole thing becomes -2 cosine of pi over 2. I'm not forgetting the pi in front. So that's pi over 2 there. The cosine of pi over 2 is the cosine of 90 degrees, and you'll remember that's 0. So that's correct. Then if I plug in, just to check over this interval, and it looks like it's following this correct pattern. So if I just check in this interval, it should be true for all x. It's true in this interval. So let's try it at 2.5, and we should get the maximum value too, right? G of 2.5 is -2 cosine pi over 3 times 2.5, which is 5 over 2, put in the fraction, plus pi over 6. Okay, so in the brackets I get what should I get in the brackets? I should get, well, I'll let you guess, but anyway, it will come out soon enough. Here it is. 5 pi over 6, that's what that becomes, and then pi over 6, and you add them and you just get pi. And that's cosine of pi is minus 1. Minus 1 times minus 2 is plus 2, which is correct. Okay, so I'll let you check the other possible values here. So, and that gives us all of the, oh yeah, the d is 0. So that's also another thing. The midline or the baseline is 0. Y equals 0 here. Okay, so that basically covers the graph of this function. And if you're asked for the phase shift, then the phase shift, or the shift in time at least, is minus 1/2. And one other thing is, in the book they mention this. They don't really explain it very well, but what they say is that the direction of the phase shift, which here would be minus 1 over 2, is the same as the sine of c when you put it in b x minus c. Okay, so if you look at this form of the, so let's write it out. C. So C is, in the last problem, it was minus pi over 6. So it's a shift to the left. But that's the same direction as the shift, as a time shift, which is C over B, which is minus 1/2. So this is a time shift. This is the phase shift. This is what I call the phase shift. I'm used to calling this the phase shift, whereas this is the actual time shift, or the x shift. In this case, x is here. Okay, there's no change in their sign because b is positive. Okay, what if b is negative? B is negative. That's what happens to the time shift. Well, if b is negative and c remains negative here, then this ratio will be plus 1 over 2. And this is the actual shift in the time direction. But then because you have a minus sign in front of the b, there's also a flipping about the x-axis. In other words, flipping about the y-axis. There's a reflection in, if you change b to minus b, in the last equation, in the last problem, for example, if you take this, it's a minus sign, instead of a plus sign. Where was the equation again? Yeah, you change the minus sign, plus to minus in front of the first term here in the argument, then that will reflect about the y-axis, right? Now with the cosine function, if you first do the reflection, then you change the sign. And then if you then do the shift, which direction should you shift it in order to get this? In order to get this phase shift of pi over 6. Phase shift has stayed the same. That's just c. C is still minus pi over 6. Well, it should still be in that direction, right? Okay, so let's see why that works. So, okay, so let's see the cases. So if you have you start with minus 2 cosine pi over 3x, and then you shift, then reflect, okay, so you do this shift in the negative x direction first, then you get minus 2 cosine. So we got what we had before, and then reflect, and that will give you the minus 2 here, or the minus pi over 3 here. With the same phase shift. So I think I might have to take back what I said. So now when you do this reflection about the y-axis by changing the sign of x, then you'll see you'll get values over this point will get changed to over here. Okay, so it will look like this in red. This third one, it will be bottom, go to the bottom right over here. It'll be shifted everywhere by in the plus direction now. Okay, so does that make sense? So the time shift now is c over b is plus 1/2, so I have to shift it to the right. But the phase shift has stayed the same. Okay. Another way of seeing this is if you first reflect and then shift, to get the same function, you would have to first shift it by minus pi over 6. No, sorry. You first reflect and then shift. So first reflecting from this one gives you this. And then you shift. But now you have to shift in what direction? You have to shift by minus pi over 6, because that's what you put in with the x. X goes, you replace x by x minus pi over, minus 1 over 2. Okay, so when you multiply that out, you then get the same, what I got in the end in the first way of doing it. Minus pi over 3 times x plus pi over 6, which is right here. So these two ways of doing it are equivalent to each other. You get the same end result, as long as you shift first by, you first reflect it. So first reflecting the graph does nothing. It just because it's an even function, it starts as an even function. We're talking about this one here, right? So this is the one that gets reflected. And so this is just the same as before. But now when you shift, you have to shift to the right. The phase shift has to be pi over 6. All right? Plus pi over 6. Let's make that clear. To the right. Shift x by, you have to be careful here, it's x that we're shifting 1/2 to the right. Shift x by 1/2 to the right. And then doing that makes this go into the argument. Everything else stays the same. And so whatever's in the argument is like this, and what's outside, I'll just repeat that. Okay, so that's the second way of that's the second way of looking at this other example, which I've drawn here. All right. Okay, so I hope that's clear. Phase shift and the time shift might be in different directions if B is depending on whether B is positive or negative. All right. So now let's look at other functions. Trigonometric functions, the tangent, for example. So again, the tangent function let's go back to blue here. The tangent function is simply y is tan x. So let's look at what that graph looks like now. So the basic graph, so we did the basic graphs for the sine of x and for the cosine of x. So now I would like to do the tangent of x. And x again is measured in radians. And so what this graph looks like, remember, it's the sine of x over the cosine of x. So whenever the denominator vanishes, then we have a problem with defining our function tan of x. Okay, so when does cosine x equal 0? Well, you remember what the graph of that looks like. You start off at 1, but you go down to 0 at pi over 2. And then you go to 0 again at 3 pi. At pi, it's equal to minus 1. You go back to 0 at 3 pi over, sorry, that should be over 2. 3 pi over 2, that's pi over 2. So it's going to be at pi over 2 plus or minus any multiple of pi. K is 0, 1, 2, etc. All right, so in particular, pi over 2 and minus pi over 2, those will be two places where the function, where cosine of x is 0, and therefore the tangent of x, since the sine of x is not 0 at those points, sine of x will be either 1 or minus 1 at those points. Then 1 divided by 0 will go off to infinity. Okay, so let's think of some values here. So as x equals 0, then cosine of x is 1, and we have 0 over 1, which is well defined, it's just 0. So we start off at 0 when x equals 0. Then when x equals, so some values here. When x equals pi over 4, then both the sine and cosine are 1 over the square root of 2, and I get the tangent is 1. So at pi over 4, I get the value 1. And then at pi over 2, it goes off to infinity. So I have actually a vertical asymptote here. And the function will go bigger and bigger as I approach that asymptote. The value of y will go off to infinity as I approach that asymptote. Now going in the other direction, for minus pi over 4, I get minus 1. Let's draw this table up here. I also remember the other values. So if you go off to pi over 2, then you go off to plus infinity. So this is, as you approach pi over 2 from smaller values of pi over 2, so from the left, then it goes up to plus infinity. As I approach, as I go in the other direction, and I go through pi over 4, minus pi over 4, I go to minus 1. Because sine of x, we saw this before, sine of x is odd, its cosine is even, therefore sine over cosine is an odd function. So this point gets reflected through the origin to this point. And then I have another asymptote at minus pi over 2. So as I approach minus pi over 2 from greater values, which I call plus like this, then this value of the function y will go to minus infinity. So here, through this point on the x-axis, through minus pi over 2, there's this line which is x equals minus pi over 2. This line is also labeled by something else, x equals pi plus pi over 2. Anyway, that's the asymptote. There are two asymptotes here. So this whole function goes between those two asymptotes like this. This goes off to minus infinity here. This goes off to plus infinity. Now if I go above pi over 2, what will happen is that the cosine of x above pi over 2 will be negative. So if I approach pi over 2 from above, then this will be negative, but sine of x will still be positive. Sine of x isn't like this, remember. So it's 1 nearby that point, close to 1. Right here. So that will mean that I will go, if I go lower in x and I approach pi over 2 from above, then I'll go down to minus infinity like this. So this function will actually come up from minus infinity if I'm going in the positive x direction now. It will go through 1, same value, minus 1, when I go through, it's going to be the same distance away from the origin, or distance away from pi over 2 as pi over 4 is from the origin. So this will be 3 pi over 4. And then when I get to 2 pi, I go through 0 again. So this whole value, I'm sorry, this should be pi. But it's the next time that sine goes to 0 is at pi. And for that value, I start repeating now. So from here all the way through all the way to infinity, and then up from infinity to here, this is repeated now. So if I keep on going, I'll get this whole shape again. And if I go in this direction, again I repeat and get that shape. So I can take the period to be from here to here, but it makes a lot more sense to take it to be from here to here, because that's all one continuous line. So this part gets repeated to here and over to here. And these asymptotes are all shifted relative to each other by pi or minus pi. Okay, so this will go off. Let me draw it like this. It will go off to infinity at x equals. This point on the graph will be at pi. Sorry, pi over 3 pi over 2. This is a value. This value pi, the graph goes through 0. So this border here, I'm trying to squish it in and make it an asymptote. Over 4, no, 5 pi over 4. All right. Okay, so now I will try to continue this next time. I've already gone quite a bit here, so I'll probably have to do an extra lecture to finish off the rest of this chapter. Chapter 8. All right, so I want to continue next with inverse trig functions. I'll do an example to review the tangent function, perhaps, but I want to talk about inverse trig functions, their graphs, as well as evaluating formulas using inverse trig functions and trig functions together. So there are a few more pages of my notes here to cover. So I think that should be possible to do in one more lecture. So I'll stop here and say Hudofis if you've been watching in the evening. Anyway, Hudofis, and I'll see you in the next, hopefully, lecture. Okay, take care.